Thank you very much, Tiffany, for the kind invitation and for this introduction. And my talk today is going to be about shape analysis, structure preservation, and deep learning. I have not tried this talk before, so I'm not 100% sure that I will be able to cover everything that I planned, but I really hope so. So I will start with an introduction on the topic of shape analysis and how this is related to other problems in machine learning. And I will give a number of examples and applications. And then we will focus on one particular problem that I've been interested in the last few years. Give some theoretical results, but maybe I will not focus so much about this. And I will also discuss shapes on manifolds. And in the end, I would like to talk about learning dynamical systems from data, and I hope you will see that this is strictly related to some of the other problems that I'm discussing today. Okay, so maybe it's not a big statement to say that Euclidean metrics are not always the most appropriate choice to deal with data. So if you want to classify data correctly, perhaps you should also think about choosing the correct metric or the most appropriate metric. So one example that I like always to take is the simple deep neural network as an example, ResNet, for classifying points on the plane. And so we have this spiraling configuration of the points, and we want to separate the blue points from the red points. And if we use a neural network, ResNet in particular, and we know that ResNet are related to differential equations, simple ODE problems, then we can think of what happens throughout the layers of the network. And what happens is, in fact, that the configuration of the point is changing throughout, and is getting into a position where the blue points can be easily separated by the red points through an hyperplane. So what happens here is that the first we have a transformation through the flow you can think of a differential equation, and then we reach a configuration in which Euclidean metrics are easy to use. So this is going to be a point that I will show or will use also later in what I'm discussing in the context of shape analysis. But similar ideas can be seen, for example, in the case of normalizing flows or other techniques in machine learning. In fact, the neural ODE paper that is strictly related to the techniques that I'm showing here is really addressing normalizing flows as part of the results. Okay, so what are shapes? What do I mean by shape analysis and what are shapes? Shapes analysis is a framework for treating complex data and obtain metrics on appropriate metrics on data spaces. Examples can be curves, time signals, surfaces, images, and you name it. It is useful for solving different tasks, for example, data classification or data generation, if you do interpolation of shapes. But one of the main applications you can say is that of object recognition. And you see, for example, here, the example of the leaves where you use contours or curves, closed curves to represent these leaves, and you want to recognize which type of leaf you are looking at. And you do that, for example, with closed curves, and you look at these curves independently on how they are parameterized, so independently of their parametrization. Okay, so what was surprising for me when I started to look into this subject is that there are a number of problems that can be cast into the context of shape analysis, and that is, and you can gain something of doing so. And one surprising thing for me was time signals, for example. So time-dependent curves, you can say. And here it's an example of which will come back also later, and it is about human motion. And these are time curves, human activities are time curves, and the configuration space in this case is a number of copies of the Lie group SO3. So it's a number of rotation matrices that essentially tell you how each of the bones in the skeleton that represents the human being here are oriented with respect to a reference point or a reference frame. So here, these are things that you do in animation applications. These are curves or data that are interested for people who are doing video games and things like that, but also for medical imaging. For example, for examining the way people walk and if they have injuries or if they have a strange behavior in their movements and so on. So the data is obtained by motion capturing, and then the processing of the data is called motion manipulation. And here are some examples, and I refer to this database also later, this database from Carnegie Mellon University, where you can see that the actors are being filmed with some markers on their suits, so that the data can be recorded properly. And another example here is an example that I found in my own university of people who are ski jumping, doing ski jump. And in this case, for ski jumpers, it's not so easy to have them wear sensors or markers like in the left picture. And here you would like to do without markers. So you have to use some AI techniques in this case in order to be able to represent the movement by means of this skeleton here. So another surprising thing for me that I have a background in differential equations is that this type of movement or this type of mechanics is not represented by differential equations necessarily, but it's just given by data. It's just given by recording data. And by these recorded data sets, you can generate new data. So no differential equations apart from very simple ones, like, for example, this one that I have here, that tells you that you can have your curves, but perhaps you are interested also in looking at their derivatives if you can get some information about them. All right. Another interesting application, which I learned from some colleagues, is this paleobiological reconstructions of joint mobility. So here, this was an interesting application for me because the Lie group that we are considering here is not simply the Lie group SO3, but is the Lie group of rototranslations, which is SE3. So this was a newcomer for us. We had the feeling that this SE3 group could be interesting, could be important for applications. But in fact, in this paper, they do apply do is to see, they have extinct animals with the bones, and they want to see what are the possible movements of the skeleton of these animals. And in the paper, they show that SE3 modeling is giving advantages over SO3 modeling. Here is another problem that is also relevant for Norwegian applications, and it is in aquaculture. So it's what you see here are on the left are hearts of salmon, and on the right are stylized or just curves that represent these different figures that you see on the left. So as you can see, the hearts are quite different from each other, but they are examined and categorized in order to study diseases of the fish. And there is a lot of interest, and there should be at least a lot of research about this in Norway. I don't know if there is, but I hope there is. So the point here is that essentially characterized diseased hearts compared to healthy hearts. And the diseases can be a lot. The hearts can look very different from each other. So the shape analysis or good machine learning tools would be quite useful here. But so far, I've told you only of curves. I want to say something about surfaces. And for two examples, one are the digits of MNIST that I will also consider later. So they are just images, and you can think of images like surfaces. And the other one is this diffusion tensor imaging of the brain, where each round point that you see in this picture corresponds to a 3x3. It's in reality an ellipsoid, and it corresponds to a 3x3 symmetric matrix, which measures the diffusion of water in the brain. So these images, if you want to manipulate them, they are surfaces, but with which are manifold value, because the symmetric matrices are building a manifold or a part of a manifold. Okay, points on the manifold I wanted to say. Other surfaces, there are numerous of them and treated in different ways. For example, if you want to do image registration of the brain or something like that. But here also you have bones and the heart and etc. So potentially there are a lot of applications. I will not show examples for everything. My scope is limited in the sense of applications, but I think that it's good for motivating the work. Okay, shapes are then unparametrized curves or surfaces. I will concentrate on curves in the explanations. The use of shapes is natural in application where you want to look at your data independently of their parametrization. If you realize that this is not what you should do, then you should give up looking at it. Then it's not necessary because looking at things independently on the parametrization has a major cost, brings a major cost into the picture. So the way we're defining this, we will look at curves then, which are C infinity, and we will require that the derivative is non-vanishing. So we look at the space of immersions. And it turns out that the space of immersions is an infinite dimensional manifold question.
Yeah, if I could. So the term shape, I was wondering whether you were thinking about that as a scale-free object. So given some
No, I don't think we don't consider scale here. No, not
yes.
for the moment. I've not thought what I should do in order for yeah, to consider that into the picture.
Mm-hmm.
But it's a good question. I mean, of course, a scale and maybe rotations, translation of the shape itself, these are also interesting invariances that you would like to preserve or to eliminate from the picture.
Just that the term shape often is interpreted as basically that feature which is scale free. A square is not coming with a length scale.
Right. Yeah, okay. But I don't think I have ever done that. So it's not going to be part of this talk.
Yeah, thanks.
All right, so we have these immersions. I was going to say that this is an infinite dimensional manifold. I will give a little bit of more information about that in the next slide. And then we consider an equivalence relations in between curves in order to define the shapes. And we say that two curves are equivalent if they differ only by a reparametrization. So if, and the reparametrization is going to be an orientation preserving diffeomorphism. So what we're doing here is to take the space of immersion and to take the quotient with respect to the diffeomorphism group. So this will be our defined shape space. Okay, so how do we look at these spaces as infinite dimensional manifolds? I'm not an expert myself in this field, but there has been a lot of work in this topic and also motivated by shape analysis, I would say. So what you do is you need to put a topology on your space, and you start with the C infinity curves, and this topology is generated by a topology, the so-called compact open topology on the continuous curves. And this compact open topology is generated by these sets W here, that send compact of functions, continuous, which send compact sets into open sets. So by means of this basis of topology basis, you can construct a topology of C and then of C infinity. And then it turns out that the immersions are an open set with respect to this topology, and therefore this is sufficient to say that this is a manifold. But what we are going to be interested in mostly is to be able to make metrics or measure distances on these spaces. And in particular, also distances on the space of shapes. So what we do is we start with a measure of distance on the shape of immersions, in this case, or say the parametrized curves with the pre-shaped space, also called. And we require this distance, provided that we are able to figure out how to do it, we require that this distance as this property here. If we reparametrize, so if we want to compute the distance in between two curves, and we reparametrize the first curve and the second curve with the same reparametrization, then the distance should not change. And it turns out that this is both essential and enough in order to have a well-defined distance on the shape space. So now if you have two equivalence classes, C0 and C1, and two shapes, and you want to find the distance in between them, then what you do is to take the distance of the first curve and to the second curve reparametrized in all possible ways with all possible orientation preserving diffeomorphisms, and take the infimum over the diffeomorphism group. So this is, of course, a very demanding task. Here's the proposition that tells you that if you start with a metric on the pre-shaped space before the quotient, which has this reparametrization invariant property, then your definition on the shape space is good, is independent on the choice of representatives. So the only problem here is that this optimization problem is quite demanding. Also, once we have discretized and we have made it into a finite dimensional problem. All right, so, but the first thing is to look into the distance on the pre-shaped space. And for this, since we are working with manifolds, one good way to look at it is to consider Riemannian metrics. So we consider the tangent space at every point to the manifold and an inner product, an appropriate inner product on each of the tangent spaces. And then it turns out that you can compute geodesics with respect to this Riemannian manifold, the Riemannian metric, which correspond to straight lines in Euclidean space. So they are the paths that connect two elements in the space P or in the manifold in the most efficient way, you can say, or the taking, provided that the 2 points are close enough, minimizing the length. And then the distance in between the two curves will be the length of the geodesics. Okay, so here is an example. Then we have two curves, the black one and the red one. And the geodesics is essentially a deformation from the first curve to the second. So this deformation here in blue that I've depicted here is essentially the geodesic in between the two curves. And the length of these geodesics will be the distance in between the 2 points. Yes?
Yeah, quickly, if I could. So the tangent space here, that's in this planar case like a normal velocity field on this curve.
You wouldn't say, no? It's tangents.
Yeah, so maybe the separate question would be, it's a Hilbert space in the sense of infinite dimension. It's an infinite dimensional vector space, this tangent space.
That's true.
Are there natural metrics that spring to mind based on the context, the application?
Yeah, okay. So I'm coming back to that, but the metrics that work are the so-called Sobolev metrics.
Yeah.
So you need to have to take into account information about the curve and also its higher derivatives in order to
not just L2, something like W12 and so on.
No, because the L2, in fact, there are some well-known results that by for example Mischer and Mumford that say that L2 doesn't work for reasons that I'm not going to go into now.
Okay, thank you. Mm-hmm.
All right, so we have a deformation here that tells, so the geodesic, what we are used from the Euclidean space is just a straight line, but here instead is a geodesic in between curves, so it's going to be this deformation. And another thing I want to do, before I tell you how I prefer to choose this metric dp, another thing I want to do is to illustrate a little bit what it means to have a reparametrization invariant measure of distance. So here you see that in the choice I've made that I've not discussed so far, the first panel here is just a deformation, the original deformation. If I change the parametrization of both the curves, which I've done in the second panel here to the right, then the deformation doesn't change. However, if I keep my parametrization as is for the first curve and I change the parametrization of the second curve, then I have, then the deformation changes. And if you don't believe me, I also plotted the two deformations in the same plot here to the bottom right in order to see that indeed they are different. So what we are going to do then is first to compute deformation, but then to optimize over all possible changes of parametrization of the second curve. Okay, let me tell you how we prefer or what is our best choice for the metric DP. The reason for this choice is very simple, is that it is a very nice and algorithmic way of computing this distance. So what we're going to do is something similar to what we did at the beginning of the talk, what I did at the beginning of the talk. So we're first going to make a transformation of the curves, and then we're going to use a Euclidean metric. So here, the transformation can be, for example, this transformation here, the square root velocity transformation, which essentially means simply that you take your curve, take the derivative, and scale it with the norm, square root of the norm of the derivative. The second option is this Q transform, that is a scale of the original curve with the square, again with the square root of the norm of the velocity. And then our distance here, dp, on the space of immersions, will be given by simply taking the L2 distance of the transformed curves. So I first transform the curves, call the transformation Q0 and Q1, and then take the difference and the L2 norm. So it turns out that this algorithmic approach is quite nice. It was invented by a number of years ago and studied already at that point. And we find that this is a very interesting or simple approach, because everybody in numerical analysis or even in data science, I'm sure, knows how to do L2 metrics or discretize and L2 metrics. Some properties of this approach. So this Q transform and SRVT, they have an important properties, which is this equivariance property with respect to the group of diffeomorphisms. So what does it mean? It means that if you first reparametrize the curve or apply, compose the curve with a diffeomorphism, and then you transform it, it is the same as first transforming the curve, then reparametrizing, apart from this scaling factor here. So this is essential in order to prove that the metric that you obtain is reparametrization invariant. There is also a strict connection in between this metric and the geodesic distance between curves. There is in the background a Sobolev type Riemannian metric, which we can call the elastic metric. Both SRVT and Q transform can be also generalized to surfaces, to embedded surfaces, and I will have a little bit of information about that later. Okay, now we go back to our main problem, which is this optimization problem on the group of diffeomorphisms. So I have my definition of distance on the shapes, and I have my optimization problem on the diffeomorphism group. Now I've chosen my favorite metric on the space of immersions, and I can rewrite the problem in this form here. And using the properties of equivariance, I can even rewrite the whole thing by means of the transformed curves Q0 and Q1 and the reparametrization. So I have still an infinite dimensional problem, optimization problem to solve. The way I'm going to solve it, I mean, there are many ways to do this. And the first way we used was to use dynamic programming. So it turns out that this problem can be, it's amenable to use dynamic programming. You can do it. But in our experience, this approach was rather expensive. So we have started looking, especially for the case of surfaces, we started looking at alternative ways. In particular, there is a paper by describing how to do gradient descent. I think I will have the references somewhere, maybe here, maybe later, I don't know. And this was very instructive for us and for the method that in the end we preferred or we proposed. So in any case, what is useful is to look at the tangent space at the identity at the of the diffeomorphism group and to be able to create a basis for this tangent space at the identity. This is useful both for describing the gradient descent, but also for our method. Okay, so let me tell you how we intend to do it. What we're going to do is to approximate or to parameterize our approximate diffeomorphism here by means of a composition of perturbations of the identity. Here, H1, HL, they are just small parameters, scalars, while F theta 1 and F theta L are vector fields, which we pick into this tangent space at the identity. So they are simple vector fields. These are given by the linear combination. This tangent space here is a linear space. So they're given by a linear combination of the basis elements. So we have a basis of this tangent space at the identity. We construct it. And then we take this linear combination, we create each of these vector fields, and then we perturb the identity by adding a scaled version of these linear combinations. And then what we do is we replace this infinite dimensional problem with the finite dimensional one, where we optimize with respect to the parameters that we use to parameterize these approximate diffeomorphisms. So this it has been inspired in how to us by the ResNet deep learning approaches. So it's very much like a ResNet. And in fact, what we did was also to implement this in PyTorch. Okay, some further comments on the way we pick the basis. There are several possibilities for the, yes, Stephen?
Yeah, sorry, it's a very interesting talk. So are there any convexity assumptions that you need on E, your energy functional, before proceeding with this?
No, this is like in neural networks. We don't do this.
Yeah, because I was.
I mean, of course, I've tried to study this, but I have not succeeded yet.
Okay, thank you. Yeah.
Yes, basis functions. For example, the easiest choice are these truncated Fourier bases, but here we have for the case of curves, we have at least these three possible choices. Here it's a slide about surfaces. So we look at the surfaces as embedded surfaces, And there is a complete analogous way of computing the Q transform and the square root velocity transform. And the scaling, before we had a scaling which was depending on the derivative of the curve, while here the scaling is given by this area factor here, the norm of this cross product in between the derivative of the surface with respect to one variable and times the derivative of the surface with the respect, or cross product of with the derivative of the surface with respect to the other variable. So it all fits. There are some problems when you go to higher dimensions compared to curves. So not first of all is the complexity and the cost grows, but also the geometry is not so straightforward anymore. But anyway, we'll see at least the algorithms, they work. In the case of surfaces, the basis we have used is simply a tensor product basis based on the Fourier basis. So again, something relatively simple. Okay, I want to show you some examples here. In this example here, we have a problem with curves. We have two curves and we reparametrize them. So it's just the same curve is just changing the reparametrization. And what we want to do is we want our algorithm to be able to reconstruct the reparametrization, which is this, this curve here. And if you look carefully, there is a black curve on top of a blue curve, means that this is our reconstruction, what we obtain. And here is the convergence of the gradient descent. So the algorithm is indeed able to reconstruct, and it's also doing quite well with respect to the approach based on gradient descent. Similar example for surfaces, we want to reconstruct the reparametrization. We reparametrize the surface, and we want to reconstruct the reparametrization. And we visualize the reparametrization with this distorted grid here. And on the left, we see the true one, and on the right, you see the found one. Okay, so since I have a background in numerical analysis, I like to see errors, and here is it's how we can show sort of convergence. We have implemented this in PyTorch, so this is single precision arithmetics. And as you can see, when we send the number of layers and the number of basis elements to infinity, we do indeed get convergence. So our approximations get better and better. And in the first row here, you see this for the curves, and in the bottom row, instead, you see this for the surfaces. Another example is this transformation in between the number 7 and the number 2 of the MNIST database, which we have done. On the top, we have a simple convex linear combination of the two images, and you see how this Euclidean geodesic in between the two images is not really a transformation or a deformation, because it makes the one number to appear and the other one to disappear, but it's not a real transformation. While by using these optimal reparametrization techniques, we get a much more realistic transformation of one surface into the other. And you can see that the optimal reparametrization is a non-trivial one. It's quite complicated. We have some expressivity results as well that tells us that indeed if we take L1 one Lipschitz vector fields, and we take enough layers, then we are able to reproduce the whole diffeomorphism group. This is results from infinite dimensional geometry, and I'm not going to say much more than that. The fact that we choose one Lipschitz vector field is convenient because this will guarantee that phi L here is invertible, and we need invertibility since we're talking about diffeomorphisms. Okay, next topic is about generalizing this to Lie groups. So far I've been considering curves in vector spaces, but it is also interesting to consider curves in Lie groups, as I showed you originally in my examples. And to do so, what you need is to, for example, generalize this square root velocity transform. And this is work we have done some time ago. So you look at the transformation. How is it? It is taking the derivative and then scaling it appropriately. And if you want to do this on manifolds or on Lie groups in particular, you have to do an extra operation, which is to bring the derivative of the curve to a common space of reference. So you need to use either parallel transport or something like that. For Lie groups, this is a little bit easier because there are some nice features in curves on for curves on Lie groups. Because if you have a Lie group G, capital G, and you take the C-infinity curves on G, you get an infinite dimensional Lie group. And its Lie algebra is connected to the Lie algebra of the Lie group G, fract G. And there is an exponential mapping in between the infinite dimensional Lie group and the Lie algebra, which is this evolution operator, which is the solution, applying the evolution operator to a curve on the Lie algebra. It means simply to solve this differential equation here with the initial value equal to the identity. So the inverse of this evolution operator is the so-called right logarithmic derivative or logarithmic derivative. And this is what you need in order to generalize the square root velocity transform to Lie groups. And this is what we have used. There are many similar nice properties to those I've described before. So for the Euclidean case, I'm not going to discuss this more, but I want to get, to show you some examples. And I also think I have little time, so I will skip this slide as well. This is about how things go when you deal with discrete curves instead of continuous. But here is the application of this Lie group approach. And what we do is we classify jumping, running, and walking animations. And in order to get this so clear classification, first of all, we take into account the geometry of the rotation group. We are careful with the reparametrization invariance distance that we pick, and we use dynamic programming to obtain this, to solve the optimization problem on the Lie group. So we have not tried the new method here. And then in order to visualize in 2 dimensions, we use a technique which is called classical multi-dimensional scaling. Okay, so last topic, if I manage to say something about it, we probably don't have a lot of time, but it's something that we have started looking into in not so long ago. And it is about learning mechanical systems from data. So I'm not going to show any videos here, but there is a video behind these pictures. So what you what we have is a person who is hanging on this frame here and swinging back and forth. And the motion capturing, this is done with markers, gives you a corresponding animation. So what we would like to be able to do, or to try to attack as a problem, is to learn the differential equations of motion of this person. And so what do we need? There are a number of challenges here. First of all, we want mechanical systems, so there will be some Hamiltonian functions or Lagrangians that we want to learn. We have constrained dynamics because we know that this data here is given as rotation matrices, but in fact you can imagine that this is a number of pendula that are describing the motion. And there are external forces, because if you don't have external forces, the guy here is not going to, the athlete is not going to swing back and forth, it's just hanging down. And there is another challenge, which is how do we provide enough data for learning, or for using learning techniques to do this. So some of these, so this is a project that my PhD student Martine Hansen is keen on trying. And we are going to use the technique of learning Lagrangians, and also use Lagrangians with external forces. So the challenge will be also to learn the external forces. When it comes to the constraint dynamics, we have already done some work, and I'm not going to say a lot of it, but this is a collaboration with my former PhD students, Andrea Leone and Davide Murari. And here we were looking at Hamiltonian systems, constrained Hamiltonian systems. So we imagine to have the trajectories of the problem, and the trajectories are lying on a manifold. In this case, in the examples we will show, we have pendula that evolve on spheres. And given the trajectory, we want to recover the Hamiltonian function. If you have the Hamiltonian function, then the Hamiltonian vector field is easy to get out of this. So here is a solution of what we get. And you see that you have some dark trajectories, dark red trajectories. In fact, we have black trajectories, which are the true vector field, and or the flow of the true vector field, and the predicted trajectory, which are the flow of the predicted Hamiltonian vector field. Okay, similar problem, but in the context of boundary value problems now, is this Euler elastica as well. We have learned the solutions. In this case, we were not interested in learning the Hamiltonian function or the Lagrangian function, but rather learning the solution of the problem to provide a way of speeding up the computations. And the challenge here is this Lagrangian, which is rather simple, but with an extra constraint. The reason why the Lagrangian is simple is that we are parametrizing with respect to arc length. So we have this extra constraint to take into consideration. And also in this case, we preserve the constraint pretty well. And we also are able to predict trajectories with unseen boundary data. So we learn on seen boundary data, and we predict on unseen boundary data. Okay, I think I will stop there. The last project is the project of another PhD student who is been interested in also learning Hamiltonians, and especially in the presence of noise. And with this, I stop. Thank you very much for your attention.